Hey everybody, Corey and Victoria here. We are the Professors DuBois, and today we're going to talk about balancing chemical equations or chemical reactions. But to get started, we probably ought to show you what a chemical reaction is.
Yeah, let's start there. All right, so we represent chemical reactions with an equation, and the equation is the reactants going to the product. So we write the reactants or the formulas for the reactants, or like the ingredients, what you're going to start with for this reaction. And then we have an arrow, and that arrow is the reaction. So it's kind of like proceeding forward in the reaction, and then we write the formulas for the products.
So there is a law of conservation of matter, and this was originally, actually I think there was a lot of talk about the law of conservation of matter, but a lot of credit goes to the scientist Lavoisier, and I think if I was to pronounce that correctly, it was Antoine. I think it'd be like Antoine Lavoisier or something like that. I don't know, but He's the chemist late 1700s, which sounds like, oh, that's so long ago, and it is, but at the same time it isn't. I mean, we're studying things here, a little over 200 years old is when we came up with this. It's not that long ago. Yeah. Anyway, back to the law of conservation of matter. This law says that we cannot create nor destroy matter. So what that means is, from an atom standpoint or an element standpoint, if there's elements in the reactants, they're going to be present in the products. Now, they might be in a different compound, but they're going to be there in the same proportion, and this is really important.
So when you go back to the reaction, the chemical reaction, you've got your reactants on one side and the products on the other. Now, this is not representative of actual elements, so we're just saying element A and B. But if we have a molecule A2, so we have two A's, so this is maybe a hydrogen or some other diatomic element, and we have another diatomic element, and we're combining them in a 1-to-1 ratio. We need to balance this. Right now we have two A's on the left and one A on the right. So that's what we mean by balancing. We have to have the same number of atoms or the same number of moles of atoms on both sides. Now, we can't change what the formula is. This A2 is A2. That's what it is. We can't balance it by just saying, oh, I'm just going to get rid of that 2 because I have one A over here. And I can't add like a subscript 2 by that A either. We have to use something called coefficients, and coefficients are large numbers that you put out in front of the formula that says how many of those molecules there are. So let's show you how we would balance this equation. So in order to balance with coefficients, this red 2 is what we call a coefficient. So for two A's on the left, I need two A's on the right, and the only way I can do that is to add a coefficient. So if I have 2 in front, that means I have 2 entire AB's. So now I have 2 A's and 2 B's, and we're balanced.
We're balanced. Okay, so this one is extremely tricky, right? Because I can't put a coefficient on that product that will satisfy the A and the B. But what you have to realize is we can put coefficients on the reactants as well. And one of the things I like to do is I like to eliminate odd numbers.
Yeah, that's a good trick.
Because you can, it's funny, you can make an odd number an even number, but you can't make an even number an odd number. And you're probably like, what are you talking about?
That's true.
So, but here's my point. I can put a 2 in front of that B with the subscript 3, and I can make that 6 B's. I just made that an even number. But you can't use a coefficient to make an even number odd. Right. So I kind of seek out the odds, and I usually start with a 2, and that'll make them an even number. So if I put a 2 in front of that B3, I've got 6 B's. Now I can put a 3 in front of the A2 and have 6 A's. I want to get them the same because on the product side, there's just a 1-to-1 ratio of A to B. So I need to get them at a 1-to-1 ratio on the reactant side as well. And some people will struggle with balancing equations, and others they'll just see it and they can do it so fast. So if you're like, whoa, that wasn't easy for me, you're not alone. Actually, I think the majority have trouble with this initially.
Yeah, And it's just practice. But this is another way, that's another technique that some people like to use, is just writing down each individual element and how many there are as you go through, and then you can change them along and make sure that they balance.
Put a big line right down by that arrow, so we can separate. Yeah, so we got to be the same on both sides of that line.
So another thing that we want to talk about with these reactions, now that we have it balanced, is that these are not only their one molecule, like 3 to 2 to 6 molecule ratio, they're also in moles. So if we had 3 moles of A2, we would need 2 moles of B3 to react completely with it to make 6 moles of AB. Now we're back to mole-mole ratios. We were talking about the mole-mole ratios within compounds. So we have 1 mole of B for every 1 mole of A. That's called compound stoichiometry, with working with that mole-mole ratio. But now we're introducing a new mole-mole ratio, which is reaction stoichiometry. And that is we have 3 moles to 2 moles to 6 moles within this given reaction.
So we can create a whole bunch of conversion factors within a reaction. We can go from reactants to products or reactants to reactants using those mole ratios.
Yeah, you can imagine where this is going.
This is a tough question. It's all written out in words and I don't have any formulas. So we'll have to proceed very slowly.
Yeah.
Aluminum and hydrogen chloride or hydrochloric acid, those are the reactants. So we'd have to write those out the way that they are in compound form, and they're going to form aluminum chloride, again words, and hydrogen gas. Now one thing I just want to point out is that hydrogen's a diatomic element. Remember, there's 7 of those, and this is where that becomes really important, because when you're just given a word, the words, and you have to write the equation, you have to realize that that is a diatomic element and write that as H2. Otherwise, you're going to have a mess of a time trying to balance your equation.
Right.
Watch those diatomics.
Right. So it's important that you make a neutral compound. So you formed aluminum chloride. Aluminum makes a +3, so that means we need 3 chloride ions to neutralize, or yeah, I guess it's kind of that charge. So we need to have a neutral charge. So that's why we have an AlCl3. So there's a lot going on with this problem just to even get started. So now you have your formulas. Now we need to balance. So I like to, one little pro tip, I like to leave my elements last. That seems to sometimes help. And I kind of look and see, so here's my aluminum out here. If I can always add any coefficient out there in front of that. That one's going to be easy. So I'm going to start with this 3 here.
That odd number.
There's the odd number.
Let's make it an even.
Okay.
That's where I'd start.
All right. Let's do it the way you start. So now we have 2 aluminum chlorides, and that means I have 6 chlorines, and I have 2 aluminums right now. So I'm going to go to the other side and look at these chlorines. So I have 6 chlorines here. In order to make the 6 over here, I can only do coefficients. I can't change my formula. So now I have 6 chlorines and I have 6 hydrogens. So I like to go to the other, so I balanced my chlorines. Now I'm going to look to that hydrogen and then go backwards. So I have 6 hydrogens. I'm going to go back to the other side, and I have 2 hydrogens here. In order to make 6, I need a 3 out front. So now I have 6 hydrogens here. And now we just have the aluminum.
Put a 2 out in front.
2 aluminums. Al. I got excited because I was going to go check.
Check.
Check, check.
It's balanced.
And now we have our mole-mole ratios.
All right, this is time where you'd want to pause the video and try to work through these on your own. They may be tricky. Look for those odd numbers. I see, with that second example, with that Fe2O3, that O3 looks like trouble to me. That a little practice goes a long way with this, and you'll find some tips along the way that'll help you get through these. So keep practicing, and here are your answers.
Your answers.
Whoa, that last one is a monster.
It is. It is. So we've done this usually when you start balancing equations, you always go to a whole number. You may see reactions with fractions as their coefficients, and that's okay. We do want you to start with whole number balancing just to get used to it. But you might see that, the fractions, and know that that's all right. So that's the end of this lecture about balancing equations.
Thanks for tuning in.
Catch you next time.